Now let us see graphs. Okay. So what is a graph? A graph is a pair of vertices comma edges, okay, where V is the non-empty set of vertices, okay, and E is the set of edges, okay. So as you can see, in vertices I have specifically written that it is a non-empty set, and in case of edges I haven't written that it is a empty set or a non-empty set. So that means the set of edges can be empty, correct? So there are different kinds of representations of the graph. So first representation is set of vertices pair, okay. Second representation is our diagrammatic representation. Okay, and the third representation is using adjacency matrix. And the fourth representation is adjacency list. Okay, so most often this diagrammatic representation is we call this as a graph. Okay, now for example, if this is a diagrammatic representation of a graph, this is vertex v1, this is vertex v2, and this is vertex v3. Okay, let us assume there are more vertices. This is vertex v4, okay, and there are some edges. So this is the edge e1, this is the edge e2, this is the edge e3, and assume that this is the edge e4. Okay, so this is actually a diagrammatic representation of a graph. It is not a graph. So mostly whenever we see something, a figure like this, then we say that this is a graph. Okay, so but this is just a diagrammatic representation. So let us see what is the first representation for this. The first representation is a set of vertices pair. Okay, now the set of vertices pair, we are going to make a pair of the vertices within which we are having edge. That means between those vertices we'll be having edges. Okay, for example, we are going to make a pair of v1 v2, because between v1 and v2 we are having an edge, and we can make a pair of v1 v3, because v1 and v3 we are having an edge. We can make a pair of v2 and v3, because between v2 and v3 we are having an edge. We can make a pair of v2 and v4, because between v2 and v4 we are having an edge. So this is a set representation of a graph. Okay, and this is the diagrammatic representation, as I have already told you. And the third is adjacency matrix representation. So in case of adjacency matrix representation, we'll be having a matrix like this. Okay, and let us suppose there are four vertices here in this diagram. So we'll be having four vertices here: v1, v2, v3, and v4. Here also v1, v2, v3, and v4. Right? Now, if there is an edge between v1 and v2, then it will be 1. Otherwise, it will be 0. Right? So if you see in this given graph, is there any edge between v1 and v1? No, there is no edge between v1 and v1. Therefore, it is 0. Now, is there any edge between v1 and v2? So if you see between v1 and v2, we are having the edge e1. Therefore, it will be 1. Okay. Now, is there any edge between v1 and v3? Yes, there is an edge between v1 and v3. This edge is e2, so it will be 1. Now, is there any edge between v1 and v4? No, there is no edge, so it will be 0. Right? So, if you see between v2 and v1 there is an edge, so it is 1. Between v2 and v2 there is no edge. Between v2 and v3 there is an edge which is e4, therefore it will be 1. Between v2 and v4 there is an edge, therefore it will be 1. Now, between v3 and v1 there is an edge, so it will be 1. Between v3 and v2 there is an edge, so it will be 1. Between v3 and v3 there is no edge. Between v3 and v4 there is no edge. Okay. Now, if you take v4, then from v4 there is only one single edge, which is to v2. Okay. Therefore, they are having one single edge, and others are 0. So this is the adjacency matrix representation for a graph. So that means whenever we are having an edge between any pair of vertices, then we are going to make it 1, otherwise we are going to make it 0, right? And the fourth is adjacency list representation. So what is the adjacency list representation? So we are going to make a array like this, right? And in each index position is denoting a vertex. For example, this index location is denoting a vertex v1, this index location is denoting a vertex v2, this index location is denoting a vertex v3, and this index location is denoting a vertex v4. Okay, now we are going to make a list here from all these things. So for example, from v1 to v3 there is an edge, so we are going to assume that there is an edge between v1 to v3, so it will be there will be a node like this, and this node will be storing v3. Now there is an edge between v1 and v2, therefore there will be something like this. So there is an edge between v1 and v2. Okay, now there is no edge from v1 to any place, therefore this will be null, right? Now if you take the second one, v2, now from v2 there are 3 edges. One edge is to v1, second edge to v3, and third edge to v4. So we have to make something like this. So one edge is to v1, second edge is to v3, and third edge is to v4, and this is null. Now from v3 we are having 2 edges, one edge is between v3 and v1, and second edge between v3 and v2. So there will be an edge between v3 and v1, and sorry, this is v1, and there will be edge between v3 and v2, right? There are only 2 edges. So in case of v4 we are only having one single edge, which is between v4 and v2. Okay, so this is called as the adjacency list representation. Now there are few terminologies related to graphs. Now let us see some of those terminologies. So the first terminology is related to directed edges. So what is a directed edge? Directed edges are denoted by the ordered pair of vertices, right? For example, if you are having a vertex here v1 and there is a vertex v2, now if it is an ordered pair, that means we can say that there is an edge between v1 and v2, but there is no edge between v2 and v1, that it is called as a directed edge. Okay, so here it is the ordered pair, and the ordered pair is v1 to v2. Okay, now in this case this v1 is called as the origin and this v2 is called as the destination, right? The second one is undirected edge. So this undirected edge shows that there is no ordered pair. For example, if we are having vertex v1 and then we are having vertex v2, then we denote an undirected edge like this. Okay, so in this case we assume that v1 comma v2, this pair is actually equivalent to v2 comma v1, right? And in case of directed edges, we can say that v1 comma v2 is not equal to v2 comma v1, right? Because there are directions which are involved. Okay, the third definition is undirected graph. Okay, a graph is said to be undirected if all the edges in the graph are undirected. Okay, for example, if you take this graph A, B, C, D, E, and assume there is a node which is F. Now in this graph there are no directions which are involved, therefore this graph is called as the undirected graph. Okay, so when an edge is connects two different vertices, then vertices are said to be adjacent to each other, and that edge is incident to both of the vertices, right? For example, if I say there is an edge between the vertex A to vertex E, therefore this vertex A is adjacent to vertex E. Okay, and here if you see, there's no edge between vertex E to vertex D, therefore vertex E and D, they are not adjacent. Okay, so in this graph, as you can see, there's a cycle, right? That means if I start from this A vertex, then I go to E vertex, and then I move to C vertex, and then I move to B vertex, and from B I can go back to A, right? This is, you can say this is a cycle, right? This is a cycle, right? So a graph may be having a cycle, a graph may not be having any cycle, right? So what if a graph which is not having a cycle, we are having a graph which is not having any cycle. So if you see, there's a graph like this, A, B, C, D and E. So this is also a graph. Now this graph is not having any cycle. You can try to find if there is any cycle. There is no cycle here. So this kind of graph is called as a tree. So this kind of graph is called as a tree. Okay. Now for example, if you take a graph like this, G, C, B, and there's an edge between D, A, and F and E. Okay, if you see this graph, there are no cycles in this graph, therefore this graph is called as a tree. Okay, now next is self loop. So what is a self loop? For example, we are having a node like this. So this node is storing some data, assume that it is A. Now if there's an edge between this node to this node itself, now this kind of edge is called as the self loop. Okay, now assume if we are having a vertex A and a vertex B, and these two vertices are having edges like this. So this is the first edge and this is the second edge, right? Now two edges are parallel if they connect the same pair of vertices, right? So here in this case, these edges are connecting A and B, right? And there are no directions here, so we can say that these two edges are parallel. Okay. Now next is the degree of a vertex. So it is degree of a vertex, right? So a degree of a vertex is defined as the number of edges which are incident on it. Okay. Now for example, if we are having this following graph, this is the node A, this is the node B, this is the node C, this is the node D, and this is the node E. Okay, and in this graph we are having some edges like this. As you can see, all these edges are actually the directed edges. Okay, now let us take a same graph which is not having any directed edge. Okay, so this is the vertex A, this is the vertex B, this is the vertex C, this is the vertex D, and this is the vertex E. Now in this graph we are having these edges, so there are no directions here. Now let us try to find what is the degree of these vertices. Okay, so as you can see in the definition, the degree of a vertex is the number of edges incident on it, right? So here if you see the second graph, this is the graph G2 and this is the graph G1. If you see the second graph, the degree of vertex A is actually 3 because there are 3 edges which are incident on it. Now degree of vertex C is actually 2 because there are 2 edges which are incident on it. Now degree of vertex D is actually 3 because there are 3 edges incident on it. The degree of vertex E is actually 1 because there are only 1 edges incident on it. Now degree of vertex B is actually 1 because there is only one single edge which is incident on it, right? Now if you take this directed graph, in this case the degree of vertex A is 0 because there are no edges which are incident on this vertex A. All the edges are going outside, no edges is coming inside, right? If you see this degree, this vertex B, then degree of vertex B is 1. Why? Because there is one edge which is inside or incident on B. If you see this node C, then degree of vertex C is actually 1 because there is one edge which is incident on C. The degree of vertex D is actually 2 because there are 2 edges which are incident on it. Now degree of vertex E is actually 1 because there is one edge which is incident on it. Okay. Now next is a subgraph. So what is a subgraph? A subset of a graph edges that forms a graph is called a subgraph. Okay. Now for example, if you are having this graph, this is the first graph which is A, vertex B, vertex C, vertex D, this is vertex E, and it may be having some edges. So let us assume these are the edges. Okay. Now if you take a subset of this graph, so assume the subset is A, B and C, and it may be having some edges. So these are the edges. Now if you see the graph G1 and the graph G2, this graph G2 is created from the graph G1. That is, we have taken a subset of graph G1. And what is this subset? Here in this case, this is a subset. Okay. So this is a subset. So we have taken this subset. Therefore, this G2 graph is actually a subgraph of this G1 graph. Okay. Now next is a path. Right? So what is a path? A path in a graph is a sequence of adjacent vertices. Okay? And a simple path is a path with no repeated vertices. Okay. Now, for example, if you see, take any of these graphs. For example, in this graph G1, if you see, we are moving from this vertex B to vertex A along with this edge, and then from vertex A to vertex C on this edge, and from this vertex C to vertex D on this edge, right? If this is the edge 1 E1, this is the edge E2, and this is the edge E3, then this pair is called a path. That means E1 we moved to E2, and from E2 we moved through E3, and we reached to the vertex D, and starting vertex was B. So this is called as a path. Okay, so this is, as you can see, this is a sequence of adjacent vertices, right? So here you can see the term which is adjacent vertices, and adjacent vertices is actually defining that two vertices are having an edge between them. So whenever two vertices are having an edge between them, then only we call them as adjacent vertices. Okay, a simple path is a path with no repeated vertices. Okay, now if you see this path here, B, A, C, D, so this is a simple path because there is no repeated vertices. Okay, now if you see, from D I can go to E, from E I can go to B. Now I started from B vertex and I reached again to the same vertex. Now this kind of path is containing is starting from one vertex and reach to the same vertex. Now this kind of path is giving us a cycle. Okay, so we can say that a cycle is a path with first and the last vertices are the same. Okay, so a simple cycle and a cycle is a cycle with no repeated vertices or edges. Okay, now for example, here in this case there are no repeated vertices. We started from B, then we moved to A, then we moved to C, then we moved to D, then we moved to E, and then we again came back to B. So as we came back to B, so this B is actually exception because we started from B and we have to end from to B to make it a cycle. But apart of B, if there are no vertices which are repeated, then such kind of path is called as a cycle. Okay. Now we can say that when two vertices are connected, for example, if we say this vertex B and this vertex D, they are not directly connected to each other using a edge, right? So we can say that these two vertices are connected to one another or each other if there is a path that contains both of them, right? For example, if here we are having a path which is E1, E2, E3, right? This path is containing both vertex B1 and the vertex D. So both vertex B and the vertex D. That is why we can say that this vertex B and the vertex D is connected, right? Now, for example, if we are having this graph, vertex A, B, C, okay, and there's some part of this graph is containing vertex D, E, F, and G, okay, and there's a vertex I. Now, this vertex I is not connected to anyone, right? Now, in this case, there is no path between the vertex E and the vertex A. So, because there is no path, therefore we can say that this vertex A and vertex E are not connected, right? But if you see, there is a path between the vertex E and the vertex F, therefore we can say that the vertex E and the vertex F are connected, right? So a graph is connected if there is a path from every vertex to every other vertex, right? For example, if you say there is a graph like this is a vertex A, vertex B, vertex C, vertex D, and vertex E, right? There's a path between A to B, there's a path between B to C, there's a path between C to D, and there's a path between D to E. Now in this case, we can say that this graph is connected. Why? Because there's a path between any two pair of vertices. For example, if you say there's a path between A to D, there's a path between A to E, and so on. Okay. Now assume we are having this graph. This is a vertex A, this is a vertex B, this is a vertex C, and this is a vertex D, and this is a vertex E. From this E we are having this edge. So these are the directed edges. From A to B we are having a edge. From B to C we are having a edge. From C to D we are having a edge. Okay. Now, is it a connected graph, right? So although this graph is looking like it is a connected graph, but it is not a connected graph. Okay. Why? Because there is no path between the vertex A to vertex E, right? And there is no path between vertex E to vertex A, right? And there is no path between vertex E to C. There is no path between vertex A to B, right? Why? Because if we start from vertex A, we can move to vertex B. From vertex B, we can move to vertex C. From vertex C, we can move to vertex D. But from vertex C, there is no outgoing edges. Therefore, we have to stop at the vertex D, right? So if you see from any of these vertices A, B, C, D, we cannot reach the vertex E, right? Therefore, there is no path to the vertex E. So this graph is not connected. Okay, and yes, this graph is connected. Now this graph is not connected. Okay. Now the next is a spanning tree. Okay, so what is a spanning tree? A spanning tree of a connected graph that contains, so you can say a spanning tree of a connected graph is a subgraph that contains, so all of that graphs vertices, not actually edges, so all the vertices should be there and it should be a single tree, so it is a single tree, so that is called as a spanning tree. Okay, now for example, if we are having this graph, this is the vertex A, vertex B, vertex C, vertex D, and this is the vertex E. Okay, and there are edges in this graph. So what are the edges? A to C there's an edge, A to B there's an edge, B to D there's an edge, C to D there's an edge, C to E there's an edge, C D to this there's an, and these are the edges. Okay, now assume that we are having this graph. Now for this graph we can have spanning trees. So what are the spanning trees for this graph? There may be multiple spanning trees which are possible for a graph. For this graph, a spanning tree can look something like this. A to B there's an edge, B to D there's an edge, D to C there's an edge, and D to E there's an edge. So this is a tree and it is having all the vertices which are connected to each other. Therefore this is a spanning tree. Okay, We can have a spanning tree like this also. So A, B, C, D and E. In the spanning tree we may be having these edges. Okay, so this is also a spanning tree. A, B, C, D and E. Right? Therefore, this is also a spanning tree. Correct? So we may be having one more spanning tree, which is A, B, C, D and E. So if you see, this is also a spanning tree. So any of these graph is not having any cycles, therefore they are a tree, and these graphs are containing all the edges of this spanning tree. Okay, and one of the frequently asked question gate is, if given a graph, what are the number of spanning trees which are possible for that particular graph? Okay, and we'll be answering that question in algorithms. The next is a directed acyclic graph. Okay, which is also called as DAG. So what is a directed acyclic graph? It is a directed graph. It is a directed graph with no cycles. Okay, for example, if you see there is a graph like this is a vertex A, vertex B, vertex D and vertex C. Now the directions are like this. Between A to B there is an edge, A to D there is an edge, C to A there is an edge, C to D there is an edge, and C to B there is an edge. Right? So if you see this graph, then there is no cycles in this graph. Now for example, if you start from vertex A, you can reach to vertex B, but from vertex B you cannot reach to any other place, right? In the same way, if you start from vertex C, you can reach to vertex D, or you can reach to vertex B, but from there you cannot reach to any other place because the directions are opposite. Okay. Now the next is a bipartite graph. So what is a bipartite graph? So bipartite graph is a graph where the set of vertices in the graph can be divided into two separate sets, such that there will be edge from one set to the another set, right? For example, if you are having this graph, this is a vertex V1, this is a vertex V2, there is a vertex V3, okay, and this is a vertex V4 and this is a vertex V5, and we are having edges something like this. Right, there can be any edges, right? So in this case, you can separate these graphs in two different sets, such that this will be one set and this will be another set, and there are no edges between the vertices of one set. That is the definition of bipartite graph, and there's no edges between this vertice of this another set. So let us suppose this is a set 1 and this is a set 2. So such types of graphs are called as a bipartite graph. Okay. So this portion is mostly asked in discrete mathematics part. So they ask for a given graph, is this a bipartite graph? Okay. So what is the best way to check if a given graph is a bipartite graph? Okay. So let us see a best way. Let us assume we are having some graph. So the graph which we are having is having these vertices, the vertex A, the vertex C, the vertex D, the vertex E, the vertex G. So this is actually the vertex F, or make it A. The vertex F and the vertex B, and there are edges like this. So this is the one edge, this is the second edge, this is an edge, there's an edge like this, there's an edge like this, there's an edge like this, and an edge like this, this, and so on. Okay, so these are the edges which are in this graph. Okay, now we have to see if this graph is a bipartite or not. So to check it, what you do, take two pens of different colors. Okay, now for example, here I am taking a pen. One pen is a green pen and another pen is a red pen. Okay, and start coloring the vertexes. Now if I color the vertex A as green, now all the vertices which are incident to A color them in a different color. So here D and C are connected to A, so we have to color them in a different color. So we have colored this D, and we have colored this C. Okay. Now take another vertex. For example, we are having this vertex E, which was not adjacent to vertex A, so we have to color it green, and all the adjacent vertices, color them red. So here I have colored the vertices F and G as red. Okay, and then the last vertex, which is B, and we have to color it as green. Right. Now if there are two vertices which are having an edge between them, and those two vertices are colored with the same color, then such kind of graph is not a bipartite graph, right? For example, if you see in this diagram, you can see this vertex, so this is maybe some vertex, and this vertex, they are having an edge between them, and they are colored with the same color. Therefore this is not a bipartite graph. Or you can see here there are multiple examples exactly for this case. Here, see, these are the examples, and these vertices are having edge between them, and they are colored with the same color. Therefore this graph is not a bipartite graph. Okay. Now next is a weighted graph. For example, you are having a graph like this: the vertex A, the vertex C, the vertex D, the vertex B, the vertex E, the vertex F, and the vertex G. Okay, and there are edges between these vertices. So these are the edges. Okay, and all these edges may be having some kind of weights assigned to them. Okay, for example, if you say here the edge between A to C is having a weight 7, the edge between A to D there's a weight 5, the edge between D to C there's a weight 9, the edge between C to E there's a weight 7, the edge between C to B there's a weight 8, the edge between E to B there's a weight 5, the edge between D to E there's a weight 15, the edge between E to F there's a weight 8, the edge between D to F is having a weight 6, the edge between F to G there's a weight 11, and the edge between E to G there's a weight 9. Okay, now for this graph we can even create a weight matrix. So how a weight matrix will look like? So here in this graph, how many vertices are there? 1, 2, 3, 4, 5, 6, 7. So it will be having 7 vertices here. So assume these are the vertices: vertex A, vertex B, C, D, E, F, and G. Again, A, B, C, D, E, F, and G. So let me just make the pair so that there will not be any confusion here. Okay. Now in this case, you can see there is no edge between A to A, so it will be 0. So there is a edge between there is no edge between A to B, therefore it is 0. There is a edge between A to C, and this edge is having a weight 7, therefore this is a weight 7. There is a edge between A to D which is having a weight 5, therefore, right, there's a edge between there's no edge between A to A, therefore it is 0. There's no edge between A to F, therefore it is 0. There's no edge between A to G, therefore it is 0. Now if you take another vertex, let us suppose we are taking the vertex B. From vertex B there is an edge between C to E only. So from vertex B to C the weight is 8. From vertex B to E the weight is 9. Otherwise there are no edges. Now if you take the vertex C, from this vertex C we are having 4 edges from vertex A, B, D, and E. So C to A the weight is 7, C to B the weight is 8, C to C there is no edge, C to D the weight is 9, C to E the weight is 7, and there is no edge between C to F and C to G. Now from D to A there is an edge which is having a weight 5, from D to C there is an edge with the weight 9, from D to E there is an edge with the weight 15, from D to F there is an edge with the weight 6. So others are 0. Okay. Now between E to A there is no edge. Between E to B there is an edge with the weight 5. Between E to C there is an edge with the weight 7. Between E to D there is an edge with the weight 15. Between E to F there is an edge with the weight 8. Okay, so there is no edge between E to E, and from, make it just clear here, and from E to G there is an edge between weight with the weight 9. Okay, now from F to A there is no edge, F to B there is no edge, F to C there is no edge, F to D there is an edge, F to F there is no edge, F to E there is a edge, and F to right, and F to F there is no edge, and F to G there is a edge. Okay, now from this G to A there is no edge. Now in case of G, if you see directly from G to F there is a edge, and from G to E there is a edge, otherwise all are 0. So this is called as a weight matrix. Okay, now it may happen if they are giving you a graph and there is no weight assigned to any edge. For example, if you are having this graph A, B, C and D. Now in this graph we are having these edges, right, and we are having the weight as 8, 7, 6. And there is no weight which is assigned to the edge between B to D. So if there are no weights which are assigned to any edge, then we assume that this weight will be 1. Right? That is why whenever we are having a graph which is not having any weight assigned to it, so we make a adjacency matrix for that graph, and in that adjacency matrix we fill 1 instead of any weights. Right? So if there is no weight which is assigned to any edge, then by default the weight is 1. Okay, so this question actually asking a lot of times to confuse the students, and students thinks that there's a problem with the question, or there's some misprint in the paper. Okay, now there is a terminology which is called as a complete graph. Now what is a complete graph? A complete graph is a graph where every pair of vertices is having an edge. For example, if you are having this vertices A, B, C and D. So if you are having an edge between every 2 pair of vertices, then it is a complete graph. Okay, now assume you are having this graph. Right? Now this graph is not a complete graph. Why? Because there is no edge between the vertex A to vertex E. So there is no edge here. That is why this is not a complete graph. Okay, and this is a complete graph. Right? And there are some few terminologies. One is sparse graph, and second one is dense graph. So what is a sparse graph? A graph which is having very few edges as compared to the number of vertices. So generally if we say that generally we can say that number of vertices log V, or you can just clearly write that a sparse graph is generally a graph where the number of edges are less than the V log V. That means number of vertices log number of vertices. Then that graph is called as a sparse graph. Okay, and a graph with relatively few possible edges which are missing, they are called as dense graph. That means there are every edge which is present, or either there are a lot of edges which are present, or either you can say there are very few edges which are not present, there are very few edges which are absent. Then those graphs are called as a dense graph. Okay.